Okay. So let me give example for Green's theorem. I not give for all of them, but for Green's theorem, and then we continue with the metric tensor. So example. This is for Green's theorem. But I mean, this is Stokes' theorem in general and in particular for Green's theorem with exterior calculus. So the example will be an area of a disk with radius r. Okay. So to properly define area, we need the volume form, which I do later. But let's do the calculation just to see all the rules we use. So consider so M is the unit ball with radius 0. So this is the set of points in R squared, X squared plus Y squared is less than or equal to R squared. So this is real, this is R. Maybe it's better to use lower one, I don't know. Let me use lowercase. Okay. And then the area of M is integral over M of the x wedge dy. This is a definition of area. And with volume forms, we all know why this exactly is the definition. And this is given the positive orientation. So this is orientation dx wedge dy, the standard one. Now, dx wedge dy is d of x wedge dy. There are different presentations, but this is one way to show it as a exact differential. So why is that? Well, if we expand it to be dx wedge dy plus x wedge ddy, which is 0. So we only get the first term. And also we have that the boundary of M is the sphere with radius I don't know it's, but let me define it that way. So this is the set of points whose square is R squared, and the boundary of M has parametrization log. I mean, not the full, but if you get the circle, you can parameterize it except for a single point or a very small interval. So it's when you calculate integrals over theoretically you should, when you use coordinates, you should integrate over everything except the small part. But We will not get into these details. So it has a parametrization. S1R is R cosine phi, R sine phi, phi is from 0 to p, 2 to pi. Okay. And then we have the following. So the area of M is integral of M dx wedge dy, which is integral of M d of x wedge dy. Now we are using Stokes theorem. So this is integral of the M of x wedge dy. This is Stokes or green. So I will call it Cartan. And especially so specifically green. Now we use now these coordinates. So this will be integral from 0 to 2 pi. So this is S, and now we are using change of variables, which intuitively means to change the interval, change the domain, and change the coordinates by substituting. So this will be R cosine phi, which R sine phi. Sorry, d of that. This is change of variables. Now we're calculating. So this is integral. This becomes a standard Riemann integral, 0 to 2 pi. And we have R squared cosine squared d phi. So R is constant, so it goes to the bottom, and d of sine phi is cosine phi. So we have cosine squared. And now we're just doing some trigonometric stuff. So R is constant, integral from 0 to 2 pi. And cosine squared phi is 1 plus, this is elementary trigonometry, cosine 2 phi over 2 d phi. And now we are using Newton-Leibniz. So this is R squared integral from 0 to 2 pi. Not integral, I am explaining. So I have phi over 2 plus sine of 2 phi over 4. This in the boundaries 2 pi 0. And this is R squared. This is 2 pi over 2. And this is 0 because sine of 4 pi is 0 and sine of 0 is 0. And this is pi R squared. Okay. We derived area of a disk. Okay. The second way to find this integral is just to use polar coordinates directly. It will become a two-dimensional integral. But I wanted to show Stokes theorem, and specifically green theorem. Okay. Okay, from this theory we can express what's called continuity conservation rules, but to have a full description we need metric as well, because for the constitutive rules. So we need um, to talk about the metric tensor. Okay, so because for now we haven't given any measures to our geometric objects, curves and things like that, or so I wanted to do this in the algebra because this is purely linear algebra, but I will define it in the world of smooth manifolds directly. So let M be a smooth manifold. G from vector fields. Did I define it? Yes, I define. Vector fields times vector fields to functions is bilinear. It's bilinear, no? So we say that G is a metric tensor, is a metric. Maybe I'll put tensor in brackets because you can only say it's a metric on M if it is symmetric. So this is property. It is symmetric, which means that for all vector fields in M, G of xy is G of yx. And it's positive definite. Now there is a generic definition which includes non-positive definite, semi-definite metrics, which are used in relativity, but for our case we will not need that. So it's easier to describe the theory only for positive definite metrics. Positive definite, which means that for all x a vector field, G of xx is bigger than 0 everywhere on Fm. So it is a positive function. And yeah, and I will say, and G of xx is 0 if and only if x is 0. So this means it's non-negative and it makes it positive definite. Okay. So okay, let me give. So the standard example is the Euclidean metric. So let's d be an integer and m is rd or subset of rd, but let's do it on the whole space. So define g of ddx I ddx j to be delta ij. So this is the canonical symbol. For EG from 1 to D. And expand by linearity. So that means that G of sum I from 1 to D fy d dxy and sum j from 1 to D fj d dx j is equal to sum k from 1 to D. This is j. This is maybe h is fk times hk. These are smooth functions. So fk and hk are smooth functions on M. So this is the flat metric on RD. So maybe I have only this example, or maybe in general. So in general, on RD, if j of ddx I ddx j is equal to gij, this is some function. G is represented by a positive definite matrix at every point. Let's call it. People usually use G as well, but let's put some symbol there. So G is G11, G1n, Gn1, sorry, D. G, D, D. And the standard metric is diagonal. So the standard metric is G is the identity matrix. This is 1, 1, and everywhere else we have zeros. Because we had Gij is delta ij, so only on the diagonal are 1s, and everywhere else we have zeros. Now, so some note, I don't know. Let me just give definitions to say. So, just to fix the notation. So, start with a smooth manifold. And G from vector fields times vector fields to functions be a metric. I should have done this in the previous definition, but we say that the pair MG is a Riemannian manifold. Riemann was the mathematician in the 19th century who created the theory of manifolds, but he did not know that you can do without metric. So he did, I think, only with metrics. And so it's called after him. Okay. So let me now have a note. Metric on M. This one. Metric on M, yeah. So let me give some note. Let MG be Riemannian. Then we can write, so G is from X M to Fn. Okay. This can be expressed, this is equivalent, gives an equivalent map. The flat operator. So the flat operator is, I don't know why I write it very ugly, but it's flat. It's from xm to the dual to omega 1m. So the flat of x is a function on vector fields. So it takes another vector field, and the result is just g of xy. This is the definition of the flat operator. So this is just the so-called curling and uncurling This is notation, but it has important properties. Yeah, but we know you call it flat and sharp in mathematics. This is the flat operator. So x and y are vector fields. And flat, it can be defined for any such function, but here is an isomorphism. So it's an isomorphism between the space and its dual. So this is the dual space. Between, okay, let me write in words. Xm and its dual omega 1 of m. Its inverse is called sharp. So its inverse is called the sharp operator. So this is flat. Is the sharp operator. Hashtag, this hashtag symbol is used from omega 1m to xm. So hashtag is the inverse of what? Something like that. Okay. And the sharp operator defines a metric on the dual space. So sharp defines a metric on forms, on one forms. Metric, let's call it g to the minus 1. Or I use g star in the paper, so let's call it g star. So g star is from two vector fields to functions. Yes. And g star of x of omega eta is given by omega of hashtag of it. Here omega and eta are in R1 forms. Now, if G has a matrix, has a representation, a matrix representation the G, let's go it with some underline in a basis d dxy, d dx1 to d dxd. Then G star has a matrix representation G to the minus 1. So this matrix to the minus 1 in the dual basis. In the dual basis, dx1 to dxd. Okay. And finally, I want to say that so we can write we usually write the following. We usually write as follows. It's not right. It's not notation. It's mathematically precise. It's not a new notation, but as follows. So G is sum E from G1 to D, G ij not dx y tensor product dxj. And so maybe I should have used upper indices, but yeah, so here upper indices and here upper indices as well.
Is this dxi?
Yes?
Basis vectors or the basis forms?
Basis forms. If so
But
this is
this G then?
this Gij. This is the metric represented. Yeah, this is how it's written. So if Jij is the inverse of Jij, is the inverse of Jij, then G star is sum I from G1 to D, G upper ij, D dxi, and D dx. Tensor product with D dxj. Now for flat and sharp operators, there is no new notation between because flat is the same as G in some sense and sharp is the same as G star. Okay. Now I don't write it in example, but in particular, so in particular, for the standard metric, we have the following. So G is dx. So we have delta ij. So this is dx1 tensor product with dx1 plus 2 dxd tensor product dxd. And G star is d dx1 because the inverse of the of the identity matrix is the identity matrix. So these are also canonical symbols here. D dx 1 plus 2 d dx d tensor product d dx d. Okay, now the flat metric is the standard one, but let's show example of non-flat metric. And for definition, so now let MG be a smooth manifold, a Riemannian manifold. Riemannian manifolds. And consider I will do this only for subspace for submanifolds, and let's do only on the boundary. Why not? S is a smooth manifold, be a smooth manifold, a submanifold. And iota from S to M is the embedding map, is the embedding. S, so the embedding is iota of S equals S for any S in S. Since it is a subset, we can map it to itself because it's against S, the bigger set. And iota, so iota S has an induced metric iota star of G, which is called the pullback metric. I think it's called pullback in general, but here it's called the pullback metric. Okay. So if J is some E from G to 1 Gij dxi tensor with dxj, then I star G equals G composed Gij composed with iota, and then we have dxi composed with iota, tensor product dxj composed with iota. So we need to change the coordinates. So basically, we change coordinates. I will show an example now. because we have too many abstract definitions for now. So M is the closed bow in 3D. So it is x, y, z in R3, x squared plus y squared plus z squared is less than or equal to 1. Now, G is dx, dx wedge dx plus tensor, not wedge, plus dy tensor dy plus dz tensor dz. This is the standard metric. Now let S is the boundary of M. So it is the unit sphere. So it is S2. So this is again x squared plus y squared plus z squared equals 1. Okay. Now so S has a natural metric iota star of S of G. Now we have to represent it because it's a two-dimensional space. It's good to change coordinates. So we will express iota star G in spherical coordinates. So let me. So x is cosine, sorry, sine theta cosine phi. Y is cosine theta, sine theta sine phi, and z is cosine theta. This means that dx is, so it's cosine theta cosine phi, the theta, so the derivative with respect to theta, minus with respect to cosine phi sine phi, so it's sine phi sine theta sine phi d phi. For y is similar, so dy is cosine theta sine phi d theta plus sine theta cosine phi d phi, and dz is minus sine theta d theta, and we don't have d phi. Here theta is from 0 to pi and phi is from 0 to 2 pi. So it is not a global. We exclude the Greenwich, but we'll show it locally how it looks like in this particular coordinate system. So now we have that iota star of G is this thing here, but with the new coordinate. So this is cosine theta cosine phi the theta minus sine theta sine phi the phi, and I will square it. Instead of writing it again, I will square it. Plus cosine theta sine phi the theta plus sine theta cosine phi the phi squared plus minus sine theta the theta squared. Okay. Now this is, I'll have here, so before the theta squared I will have cosine squared theta cosine phi squared theta, and here I will have cosine squared theta sine squared phi the theta with the theta. Now I will compute the theta with the phi, so this will be cosine. So this will be this time this, so it will be plus, here we have minus cosine theta cosine phi sine theta sine phi, and here I will have this with plus cosine theta sine phi then cosine theta sine phi sine theta cosine phi, and I will have this for both the theta with the phi and the phi tensor with the theta. Oh, sorry, here I forgot to put in the first term. I forgot to put plus sine squared theta. Because of this. And the final term will be with respect to the phi, so I will have sine squared theta sine squared phi plus sine squared theta cosine squared phi, and I will have the phi with the phi with the phi. Okay, from here we have cosine squared sine squared, only cosine theta remains, and then with sine squared theta only one. So this is the theta plus the theta. This is 0. We have minus something plus the same thing, and here we have sine squared theta because this cancelled. So we have this is plus sine squared theta cosine d phi wedge d phi. So this is a non-flat metric. Non-flat metric. Because of this term, this sine squared. No, I mean you have to calculate Christoffel symbols and curvature things like that to see that it's not flat, but it's non-flat. As a matrix, we have let's go with I don't know. If let H is I star G, then H is the following matrix, then in spherical coordinates. We have the following: H equals, so we have here 1, we have 0 there, and here we have sine square of theta. And H to the minus 1 is 1, 0, 0, 1 over sine square of theta. So this is on forms. So that means that H minus 1 is d theta, tensor product with d theta, plus 1 over sine squared theta d phi, which d phi. This example is given in the preprint in the last section before the conclusion, of course, which is for simulation example, because I use it for one example. Okay, now let's define the volume form. So or maybe as what orthonormal basis. Before that, I'll do volume form next part. Let Mg be a Riemannian manifold. Of dimension d, so dimension of M is d. And we have now maybe sometimes there are no global vector fields that are orthogonal, but locally there are. So consider some vector fields in omega, no, in X. Okay. And we say that x1, xd is an orthonormal basis, orthonormal basis of the space of vector series if gxi xj is delta ij, or in this interval here. Okay. Let me just write it. Oh, okay. No. Not 2, because you have d theta with d phi and d phi with d theta. It's not times 2. Okay. Can I erase it? So I'll leave this for now, the final result. So examples. Okay. It also, okay, it induces, it's dual basis, it's dual, and this in brackets, it's dual basis. Let's call it I don't know, omega x, okay, x omega 1 to omega d is orthonormal for the inverse metric G star on omega 1 m. So the first is trivial, which is the standard metric. So n is RT, well, D is integer. G is the standard metric, so G is sum from 1 to D dxy, which dxy. Then d dxi, d dx 1 d dx d is an orthonormal basis, maybe for xm, and dx1 to dxd is an orthonormal basis for the dual, for omega 1m. So this is 1. 2. 2 is non-global result. So locally on a sphere, on the unit sphere, so in spherical coordinates. So because we cut the Greenwich meridian, it's not globally. In fact, there is one theorem that says that there is no vector field on a sphere that is never zero. It's called Hairy-Bow theorem. It's something like your hair curves in some way and it's changed direction in some sense.
You cannot comb your hair so that all the you are not always going to get a point.
Okay.
That is
It-
from where the hair goes out.
in so locally on the unit sphere, we have d d theta, but then we have so this is 1 over sine theta d d phi. Why? Well, because if we multiply this thing with itself, we have to multiply by sine squared, and now it becomes 1 when it's divided by sine theta. And so if I multiply this with itself, it will be 1 over sine squared theta, and the metric on d d phi, which is sine squared theta, is an orthonormal on xm, and the inverse, because this is a diagonal metric, we don't have to invert matrices in the hard way, but only the diagonal. So theta and sine theta d phi is orthonormal basis for, maybe not on, for omega 1 m. Okay, let's make a break now. If there aren't any questions. Okay.